As of this morning, May 23rd, 2026, NASA's Perseverance rover on the surface of Mars and helioseismic echo data from ESA's solar orbiter have together confirmed that large magnetically complex sunspot regions currently lurking on the far side of the Sun are rotating directly into Earth's line of sight, and they are approaching the eastern solar horizon right now. This is not a forecast built on models, it is a measurement. Instruments that listen to the Sun, the way seismologists listen to the ground beneath a fault line, have detected them through the star's own interior using sound waves that travel through 4 million kilometers of plasma and bounce back with a signature of concentrated magnetic fields so intense they suppress the Sun's own convective motion. They are there. They are active. And within days, the geometry of the solar system will place them pointed directly at Earth. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: USGS, NOAA, the Smithsonian Global Volcanism Program, NASA, ESA, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us, but that is not even the complete picture. It is the opening chapter of a window, a period of days in which Earth will find itself in the direct strike zone of solar regions whose magnetic complexity has not yet been fully characterized because they have not yet been fully seen. Scientists at NOAA's Space Weather Prediction Center posted a statement on May 18, 2026, that carried a sentence deserving of very careful reading. Solar farside imagery from NASA. Solar orbiter means the forecast could change for May 20th and beyond. That statement was issued 5 days ago. What it described has now arrived. And what arrives with it is a risk architecture that the modern world is profoundly structurally unprepared for. The Sun is not behaving unusually for this point in solar cycle 25. That is precisely the problem. Solar cycle 25, which forecasters initially predicted would be a modest, unremarkable cycle, has instead run significantly more active than those initial projections indicated. The solar maximum window, the peak period of the cycle's activity, is passing through now in 2026, and the deep pattern of this cycle, observed across months of data, is that the most active regions have not announced themselves gently. They have emerged, grown rapidly in magnetic complexity, and fired before forecasters had time to fully classify them. Region AR4366, which produced an X8, 3 solar flare, the strongest of 2026 at the time. In February, grew so rapidly in just a few days that specialists at NOAA described it as a volatile active region. AR4436, the region now rotating off the western limb and still firing M-class flares from behind the solar horizon, it produced an M5. 7 flare on May 10th, 2026, that knocked out high-frequency radio communications across the entire Atlantic, and it has continued generating flares even as it departs our field of view. On May 22nd, 2026, it fired an M2, 4 flare that peaked at 10:29 UTC and triggered an R1 class radio blackout over Morocco. That was yesterday. The region responsible for that blackout is now behind the limb, and it is apparently powering up again. Think about what that means in concrete terms. A radio blackout over Morocco, an R1 classification, that is the lowest category on the NOAA radio blackout scale, the first rung of a 5-step ladder. The region that caused it is the one departing, the one whose strength can no longer be fully measured because geometry has taken it away from our instruments. And the regions now approaching from the other side, the eastern horizon, are the ones whose magnetic complexity, according to NASA Perseverance imagery and helioseismic holography data, has not yet been fully defined. The Earth-facing side of the Sun is currently described by space weather specialists as quiet. That word, quiet, carries a specific and important weight here. It means that right now, today, the threat is not from what can be seen. The threat is from what is arriving. The system is not inactive, it is accumulating. To understand what that accumulation can mean, it is necessary to travel backward through the record to the morning of September 1st, 1859. A British solar astronomer named Richard Carrington was at his telescope, carefully sketching an unusually large and complex cluster of sunspots, when he witnessed something that no astronomer had ever recorded before. The sunspot region suddenly and briefly flashed with an extraordinary white light, a light so intense it could be seen against the full, brilliant disk of the sun itself. Carrington noted the time. He noted the shape of the flash. He sent word to a colleague who confirmed the observation from a different location. 17 hours later, not days, not weeks, 17 hours, a coronal mass ejection carrying billions of tons of charged particles slammed into Earth's magnetic field at a velocity that modern estimates place between 2,000 and 3,000 kilometers per second. The geomagnetic storm that followed reached a Delsty index, the measure of how severely Earth's magnetic field was compressed and distorted, that modern researchers estimate may have reached minus 1,560 nanotesla. For comparison, the most powerful storm of the modern instrument era, the May 2024 event, reached a DEST of minus 412 nanotesla and was classified as a G5, the most extreme category on the NOAA geomagnetic storm scale. The Carrington event, by the best available estimates, was 4 times more powerful. The telegraph operators working across Europe and North America that night found their equipment sparking, catching fire, and, most astonishing of all, continuing to transmit messages even after they disconnected the batteries, because the geomagnetically induced currents flowing through the wire were sufficient to power the lines on their own. Auroras were visible from Cuba, the Bahamas, Jamaica, and Hawaii. Miners in the Rocky Mountains woke in the middle of the night convinced the sun had risen early. This has already happened once, and the record of it is still preserved in the historical documents, in the ice cores, and in every serious risk assessment that any major institution has conducted on the subject since. What is the record of those assessments? In 2013, Lloyd's of London and the American research firm Atmospheric and Environmental Research published a joint risk model for a Carrington-equivalent storm, striking the present-day North American electrical grid. The headline number in that report is an economic cost estimate of between $600 billion and $6 trillion in a single country for a single event. The scenario modeled a geomagnetic storm of equivalent magnitude to 1859 hitting the Atlantic corridor grid, with the highest concentration of risk between Washington, D.C. and New York City, across the Midwest, and along the Gulf Coast. Between 20 and 40 million Americans would lose electrical power. The duration of that outage, and this is the number that demands full attention, would range from 16 days at the most optimistic end to 1 to 2 years at the upper end, depending entirely on how quickly extra-high voltage transformers could be replaced. These are not standard consumer items. They are custom-built, they are large, they weigh hundreds of tons, and the global manufacturing capacity to produce them is measured not in weeks, but in years. Abraham Loeb, the chair of the astronomy department at Harvard University, has placed the total global infrastructure damage of a Carrington-equivalent event at between $2 trillion and $3 trillion. And he added something that does not appear in the press releases, but that the data fully supports. Because human civilization becomes more dependent on electromagnetic infrastructure with every passing year, the economic damage from such an event would be even greater in the future than it is today. Here is where this account becomes genuinely significant. Not because it introduces a speculative scenario, but because it connects 2 things the data confirms are simultaneously true right now, on May 23rd, 2026. First, solar cycle 25 is running hotter than forecast. The decline phase from solar maximum is underway, and solar astrophysicists who study this field, among them Ryan French of the Laboratory for Atmospheric and Space Physics in Boulder, Colorado, have stated in verified published assessments that the largest solar events historically occur during this declining phase, and that further strong events are expected through 2026 and perhaps 2027. Second, the critical early warning infrastructure that would give grid operators and satellite controllers the few hours of notice they need to take protective action, the aging monitoring satellites positioned at the L1 Lagrange point between the Earth and Sun, has been described by space weather experts as operating past planned mission life. The gap between knowing the risk and fully preparing for it remains wide. Transformer hardening is expensive. The satellite industry has invested in resilience for individual spacecraft, but the sheer number of satellites now in orbit, numbering in the thousands, including the mega constellations now essential to global communications, means the aggregate exposure has grown dramatically, even as individual vehicles have become somewhat more resistant. Consider a city. Consider Karachi, Pakistan, with a population of approximately 16 million people, the financial and commercial hub of one of the most densely populated nations on Earth. Karachi depends on a power grid that has, under ordinary circumstances, been described by its own regulators as strained. It depends on communications infrastructure, cellular networks, satellite uplinks, GPS-dependent logistics chains, to move goods, to coordinate hospitals, to operate its port, which handles a significant fraction of Pakistan's imports and exports. The people of Karachi are not thinking about the sun this morning. They are navigating traffic, opening shops, treating patients, loading containers. They are living inside an electromagnetic infrastructure as invisible to them as the air they breathe. What a Carrington equivalent event would mean for Karachi is not a data question. The data cannot fully capture it. But the data does show that geomagnetically induced currents strong enough to collapse the Hydro-Quebec grid in 1989, a grid serving approximately 6 million people, which went dark for 9 hours, would reach every latitude simultaneously, and the regions with the least grid-hardening investment and the fewest technical resources to restore large transformers would face the longest recoveries. The question those 16 million people would ask, if they had access to the data in front of us right now, is not a complicated one. It is, does anyone watching the sun know we are here? Now consider what connects the sun to the ground beneath the city in ways that are not only electromagnetic. Earth's magnetic field, the shield that deflects the most energetic particles of a coronal mass ejection and distributes the geomagnetically induced currents across the planetary surface, is itself generated by the motion of liquid iron in Earth's outer core. That field is not static. It fluctuates with the solar wind on timescales of minutes and hours. It has a known measured weak point, the South Atlantic anomaly, a region roughly above South America and the South Atlantic, where the field is measurably thinner than elsewhere, where satellites passing through it already receive elevated radiation doses sufficient to cause intermittent hardware failures. When a major geomagnetic storm arrives, the particles that would normally be deflected into the polar regions penetrate deeper at all latitudes, and deepest of all through that anomaly. The satellites that pass through it, which include a substantial fraction of the low Earth orbit constellation, face higher radiation loads during the storm period. This is not a hypothesis. This is documented in the satellite anomaly record. The connection between solar output, geomagnetic field geometry, and satellite performance is a single system. What moves in one place sends its signal outward to places no one is watching yet. The other connected system that deserves attention here is the one that governs the upper atmosphere, the ionosphere, through which all high-frequency radio communications travel. The ionosphere is not a fixed layer. It is a dynamic, electrically charged region of the atmosphere that changes density and altitude in response to solar radiation on timescales of minutes during a flare event. When an X-class flare reaches Earth at the speed of light, 8 minutes from the solar surface to the top of the atmosphere, it floods the sunlit side of the ionosphere with a surge of X-ray and ultraviolet radiation that dramatically increases the electron density in the lowest layers of that region. What that means for radio communication is that high-frequency signals, which travel through the ionosphere and reflect off it to reach over the horizon targets, are suddenly absorbed rather than reflected. The signal does not go around the Earth. It goes into the ionosphere and it stops. This is what an R-class radio blackout is. NOAA classifies them from R1, the minor blackout affecting some shortwave radio users, to R5, which corresponds to a complete high-frequency blackout on the entire sunlit side of Earth for a period of hours. The flare on May 10, 2026 from AR4436 produced R-class blackouts across the Atlantic. The region that caused that blackout is currently behind the limb, apparently rebuilding magnetic complexity. The regions now approaching from the eastern limb are uncharacterized. The question is not whether the pattern will continue. The question is when the next eruption will be Earth-directed, and how large it will be when it arrives. There is a city on the coast of New South Wales, Australia. It is called Newcastle. Its population is approximately 300,000 people. It sits at a latitude that would place it within range of enhanced auroral activity during a major geomagnetic storm, the kind of activity that in May 2024, during an event that reached a D/A of minus 412 nanotesla, produced auroral displays visible from the United Kingdom, India, Tasmania, and as far south as several Australian states. The residents of Newcastle who looked up at the sky during that event in 2024 saw something almost no living person had seen from that latitude before. They saw the atmosphere light up with a color generated by charged particles forced into the upper atmosphere by solar wind pressure that had stripped back the usual magnetic shield. It was extraordinary. It was also a G5 storm. The Carrington event was, by best estimates, 4 times more powerful. What it produced in the sky over Newcastle in 1859, if anyone had been watching, would have been visible at noon. The question those residents in Newcastle might ask, if they understood the system the way the instruments describe it, is not whether this is theoretical. It has already happened. The geological record holds the evidence. The historical record holds the testimony. The risk models hold the numbers. And the instruments monitoring the eastern solar horizon right now are telling us that something is coming, something whose full character has not yet revealed itself because it has not yet fully rotated into view. The monitoring is in place and detection is possible, but prediction is not. That sentence needs to be understood in its full weight. The networks of ground-based observatories, the GOES-19 satellite, NASA's Solar Dynamics Observatory, GSA's Solar Orbiter, and NASA's IMAP spacecraft, which achieved its operational orbit around the Sun-Earth L1 Lagrange point after launching in September 2025, together provide a monitoring infrastructure more capable than any that has existed before. Helioseismic holography allows scientists at the National Solar Observatory to detect active regions on the far side of the Sun days before they rotate into view. by listening to how those magnetic concentrations distort the propagation of sound waves through the solar interior. NASA's Perseverance rover on Mars, operating from a different angle in the solar system, has been used to image sunspot activity invisible from Earth's perspective. These are genuinely remarkable instruments operated by genuinely rigorous scientists. And what those scientists choose their language carefully to say is this: the forecast could change. That careful language is itself the warning. Not could be catastrophic, not will be dangerous, could change. From the NOAA Space Weather Prediction Center on an official government website on May 18, 2026. Scientists choose their language carefully here, and that careful language is the most precise statement they can offer about a system that continues, even now, to exceed the confidence intervals of every model applied to it. What does that mean for the satellite communications infrastructure that the world depends on without knowing it depends on? There are currently thousands of active satellites in orbit around Earth. The mega constellations, Starlink and its competitors, providing low-latency internet access to users on every continent, number in the thousands of vehicles alone. GPS satellites, on which aviation, shipping, agriculture, financial markets, and emergency services depend, occupy medium Earth orbit. Communication satellites in geostationary orbit carry television, phone traffic, and data across ocean basins. Military early warning satellites watch the skies. Weather satellites provide the data from which every forecast, including space weather forecasts, is derived. Every single one of those assets is vulnerable to a sufficiently powerful geomagnetic storm, to the elevated radiation environment of a severe solar energetic particle event, and to the atmospheric drag increases that accompany geomagnetic disturbances and that alter the orbital mechanics of low-altitude satellites in ways that require constant correction. In February 2022, a geomagnetic storm at the moment of a Starlink batch deployment caused elevated atmospheric density that increased drag on the freshly launched vehicles before they could reach their operational orbits, and approximately 38 of the 49 satellites in that batch were lost. That was not an X-class flare event. That was a moderate storm. Minutes are not hours. And in this context, the difference between the warning window available to satellite operators and the time available to act is everything. The 1989 Quebec event deserves its place in this account because it is the event that, more than any other, forced the modern power industry to confront what solar weather can do to terrestrial infrastructure. On March 13, 1989, a coronal mass ejection, the product of a series of X-class flares that began days earlier, struck Earth's magnetic field. The geomagnetically induced currents that followed overwhelmed the Hydro-Quebec electricity transmission system. The entire province of Quebec went dark in approximately 92 seconds. 6 million people lost power. The blackout lasted 9 hours. Economic losses were estimated in the hundreds of millions of dollars. Transformers and other high-voltage equipment across North America and in parts of Europe experienced anomalies and damage. And here is the number that places the 1989 event in its proper context within this story. The 1989 storm reached a KP index of approximately 9, a G5, the highest category. The May 2024 storm also reached KP9 with a DST of minus 412 nanotesla. The Carrington event, 165 years earlier, was estimated to have reached a DST of minus 1,760 nanotesla. The 1989 event that put Quebec in darkness for 9 hours was a fraction of the power of what happened in 1859. The question is not whether, the question is when. What is known with certainty as of May 23, 2026 is this: AR 44436, the sunspot region that fired an M5. 7 flare on May 10th triggered Atlantic radio blackouts, continued firing through C and M-class events through May 21st and 22, and appears to be recovering magnetic complexity even as it rotates behind the western limb. That region will return to the Earth-facing hemisphere in approximately 2 weeks. The sun rotates. Any given point on its surface takes approximately 27 days to complete a full rotation as seen from Earth. What rotates out of view comes back. And what is currently approaching from the eastern horizon, the large fiery sunspot regions detected via helioseismic holography and Perseverance imagery, described by space weather monitors as approaching the eastern solar horizon and expected soon to rotate into view, those regions carry an energy budget that the instruments have detected but not yet fully characterized, because the full detail of a sunspot group's magnetic topology can only be resolved once it is on the Earth-facing disk and observable in high-resolution solar imagery. Until that moment arrives, the forecast carries the honest qualifier that science requires when confronting genuine uncertainty. It could change. And so the instruments watch. And the satellites in the L1 orbit send their data streams, and NOAA's forecasters update their 3-day outlooks. And the world continues to function on the assumption, the reasonable historically mostly justified but not guaranteed assumption, that the sun will not, in the next window of days, deliver an event large enough to interrupt the electromagnetic systems that move food, coordinate medicine, process financial transactions, guide aircraft, and connect the approximately 8 billion people on this planet to one another and to the information that governs their lives. The sun has been burning for approximately 6 billion years. It has produced events equivalent to the Carrington event on a cycle that geological and historical records estimate at roughly once every 500 years, though smaller storms of severe but not extreme intensity occur on timescales of decades. The last time a Carrington equivalent storm struck Earth directly, the most sophisticated electromagnetic system humans had built was a wire carrying Morse code. Today, a single data center failure in Frankfurt or Singapore or Virginia triggers consequences that ripple across continents within seconds. Today, the GPS signal that keeps a container ship on course across the Pacific is the same signal that synchronizes the timestamps on financial market transactions and tells an automated farming combine where to drive. Today, the early warning window between the detection of a major coronal mass ejection at the L1 Lagrange point and its arrival at the upper atmosphere is measured in minutes to hours, not days, and the transformers that would need to be protected or replaced if a Carrington-level event overwhelmed them take years to manufacture. The sun does not operate on a political calendar. Solar cycle 25 is running more active than forecast. The largest events historically occur during the decline from maximum, and specialists have confirmed we are in that decline now. The far side regions, confirmed by helioseismic holography and planetary imaging, are rotating into the Earth strike zone. The instruments are showing this in real time. What the sun has been doing for 6 billion years, it will continue doing. What it did on September 1st, 1859, it will do again. The only variable is the nature of the civilization standing in the path of the next full halo coronal mass ejection. When the geometry of the solar system and the accumulated magnetic tension of an active region finally align in the way they aligned on that morning more than a century and a half ago, when Richard Carrington looked through his eyepiece at a cluster of sunspots and watched the sun write its signature in white light across the face of the sky, and had just enough time to note the hour before the world changed.